Welcome to the new Transatlantic Cable, a tripartite civil engineering history webinar series. The webinars are coordinated by the History and Heritage Committee of the American Society of Civil Engineers, the National History Committee of the Canadian Society for Civil Engineering, and the Panel for Historical Engineering Works of the Institution of Civil Engineers. Today's installment, recorded on September 27th, 2023, features Linda Newton and Ken Holmes on Double Double, the history of the Bailey Bridges built by the Royal Canadian Engineers.
Hello and welcome. I'm Cole Bedford, a member of the American Society of Civil Engineers History and Heritage Committee. I'll be your host for today's tripartite New Transatlantic Cable Civil Engineering History webinar. We have a fantastic agenda planned for you today, but first a word about the tripartite program. As an attendee of today's webinar, you will have an opportunity to apply for a Professional Development Hour certificate. To document your attendance, I will provide you with 2 code words, the first of which I will share in just a moment. Then we'll introduce our speaker, Linda Newton, who will make her presentation, Double Double, the history of the Bailey Bridges built by the Royal Canadian Engineers. We will have some time for a good discussion, including question and answer session afterwards. Lastly, I'll share the second PDH certificate code word, and then we'll wrap up. The ASCE, CSCE, and ICE are learned societies created to develop and maintain high standards of civil engineering practice. The intent of the tripartite New Transatlantic Cable history webinars is to enhance interaction between the societies and their members and recognize that civil engineering history crosses international boundaries. The talks are to be on topics that involve at least 2 of the participating societies. And here's your first PDH code word, McCullough. Please write this down or take a screenshot. To receive your certificate, you must complete a survey that will appear at the end of the webinar when the Zoom meeting closes out. You will need to select 2 code words as part of that survey. It is now my pleasure to introduce our presenter. Linda Newton is a fellow of the Canadian Society for Civil Engineering and a member of the CSCE National History Committee. She is also a retired member of the Canadian Military Engineers. Linda, the floor is all yours.
I'm very excited today to be a part of the tripartite webinar. Also, I have my co-author, Lieutenant Colonel retired Ken Holmes. Ken is former commandant of the Canadian Forces School of Military Engineering, and he also holds the honor of being the CME historian. So Ken contributed greatly to this presentation and to the paper upon which it was based that we presented last year at the Small to Medium Span Bridge Conference here in Toronto. But enough of that. So let's get on to today's webinar. I've always been passionate about Bailey Bridges, mainly in part from the history behind them, but also having built one way back. This particular bridge that you see in this slide, if any of you are from Southern Ontario, may recognize it as the definitely over-designed Bailey Bridge that spans a small gap that leads into Casaba Winery in the Niagara-on-the-Lake region. The title of the presentation perhaps will have some of you captivating. Double double, what's a double double? Well, to the average Canadian, the words double double, you might think of this Tim Hortons cup that you see on the right side of my screen. But to a military engineer, anybody that's built a bridge, a Bailey Bridge certainly, it means something completely different. It's a type of Bailey Bridge, and you'll find out a little bit more of that in a moment. But why is the Bailey so special? I mean, it's a bridge. It's a modular bridge, so what? Well, it was considered one of the most important engineering contributions to the Second World War. It was praised by Montgomery, Churchill, and the impact of this bridge just cannot be overstated. And I think for me, when I was doing the research into the paper, one of the most evocative statements I came across was from a young engineer who was at the Battle of Termoli in Italy. And he said, "In the terror of Termoli, men bought time with their lives. It was the bridge and the bridge alone which made victory possible, in the nick of time which had been bought so dearly. So why the Canadian military engineers, and why is this bridge so special to Canada? Well, you're going to find out. So the presentation isn't completely about the Royal Canadian Military Engineers. Obviously, we have to set some context and go into the Bailey Bridge and its design and what was so unique about it. Give you a bit of a background about the Royal Canadian Engineers. Some of you may know. I'm sure we have quite a few engineers listening. And then we'll talk about why it was so special to World War II and what made it what it was. And then realize, as many of you have seen this bridge and not know that it is still out there and not realize what it was. So we'll look at that. So to come back to the Bailey Bridge and to come back to the role of military engineers, whether they're the Royal Canadian Engineers, whether they're the Royal Engineers in the UK or the Engineer Corps in the US, the military engineers' role is to support mobility of friendly forces and deny that mobility to the enemy. So in times of conflict, engineers build roads, they build bridges, and at the same time they destroy them so that the enemy can't use them. Now, the design of the Bailey Bridge was first proposed by Donald Bailey in 1936. He was sketching on the back of a napkin. He was a model bridge enthusiast, and he worked for the Experimental Bridge Establishment in the UK. Now, as the war continued, people looked at his design and went, "That's really nice, Donald. Now go away and do what you normally do." But as the war continued and the Allied forces started to gain ground and the momentum started to shift, they started to consider the invasion of Europe. And there were two places they were going to invade Europe, Italy, and also hopefully landing at Normandy. And obviously, the retreating forces, their engineers would be blowing up those bridges. So you needed to have some means that the advancing forces could quickly get over those gaps, whether it was over a canal, over a river, whether it was over a tank ditch or something they had constructed to impede mobility. And the retreating Axis forces destroyed virtually every bridge to delay the advance. So replacement bridges needed to be capable of supporting troops and the loads they had to carry, whether it was just troops walking across that bridge or whether it was tanks. And the World War I bridging equipment they had was just not able to support that load capacity. As you can imagine, tanks developed quite significantly from what you saw in World War I to what you started to see at the end of World War II. And the design could not be upscaled to meet this demand. Back to Mr. Bailey and his earlier idea. So when Bailey had been pondering about this bridge, he came upon these 5 principles that you see here. Now think about this, we're wartime. So availability of materials, certainly what was available in the UK, lightweight materials were scarce. They'd been used for vehicles, for weapons, for aircraft, ship construction. So many such as aluminum or aluminium couldn't be used. Then we have to think about manufacturing. He needed to have something that could be manufactured using simple engineering practices, but by many companies. This was a design that then had to be scattered throughout the UK. And in the end, over 600 companies actually wound up building the components to this bridge. And the tolerances had to be such that those parts could be interchangeable. Again, thinking back, this was going to be a giant mechanoset. The bridge could be put up and it could be taken down. And if enough foothold was achieved on the continent, then you'd want to be able to manufacture it locally as well. And then the weight. Now, it needed to be able to fit into a general service vehicle, which was a truck. And it had to be capable of being lifted by a 6-person team. Because again, you're at the front, you're fighting, you're not going to be able to bring up a lot of vehicles. You're not going to have equipment and cranes and things that you can use to construct this bridge, nor do you have the time to get them in place. So part of this construction was that no part could exceed 600 pounds. The flexibility. Several configurations were probably going to be used. Now, if you think about this, the Rhine River is quite wide. The Arno, the Seine, many of these rivers, the Marne, were wide. And so it had to be strong enough to span these various gaps, including rivers such as these where you couldn't construct piers, or perhaps the piers that were there could no longer be used. And so it led to 6 configurations that we'll look at a bit later on to support these different loads and spans. And then there was a concept of ease of construction. It had to be able to put up and take down fairly quickly in as short a period as possible. So no on-site manufacturing of components, and it could be launched under any condition from one side of your gap, because you did not want to have your friendly forces obviously on the other side of your gap. So what did the bridge look like? So this final design had 28 welded steel parts, There's some discussion as to whether it was 29, but the consensus is 28 parts that you can see here, varying from things such as the stringers, the transoms, the panels. The panels were the key component. 9 parts were required for the launching structure, and so you can see that on the bottom left of your screen. If you can read the base plate and where it says bearing, that was the roller, okay, and that was the launching structure. And then there were 17 parts for the actual bridge itself. And so the panels were 10 feet long, 5 feet high, and weighed just under 600 pounds. And then you had these cross girders that were 18 feet long. And if you'll notice, you can see holes in them, and that's so that they could be transported with lifting bars so that the troops could lift them up and transport them to where they needed to go. And then you have the stringers. And so the skeleton was assembled on a series of these rollers that you see here. And then as the assembly progressed, it was gradually pushed across the gap until it reached the far side where it could then be jacked down off the rollers and you could finish the construction. So what you see in the bottom right of your screen is the Bailey Bridge, and you can see this launching nose, which is much lighter than the main part of the bridge. And that's what will be pushed across the gap. Now, what was remarkable about this bridge is that an engineer troop comprised 40 men at the time, and they could assemble under perfect conditions a 24-meter or 80-foot bridge in about 4 hours by day and about 8 hours by night. And they could push that bridge across the gap. Larger bridges, you may need to bring up a small dozer to help, but that was the extent of what was needed at the time for Bailey's Bridge. Here's a few pictures from the archives of some parts. So you can see on the top left, 6 sappers carrying the panel. And you can start to see here in the middle picture, you see the main part of the bridge where this got 2 panels and they're joined together by bracing at the top. But in the middle picture, at the very front of it, you can start to see that roller, and that's the nose that was going to be launched over the gap. And this picture on the bottom right is as an example of what that bridge would look like. I think this was when they were doing a training in one of the bases, perhaps, to learn how to construct the bridge. So now think back to that double-double word. So the configuration of the bridge became known by how it was built. So a single truss, which meant it had 1 panel wide, and it was 1 panel high, was a single. If it was 2 panels wide and 1 panel high, it was a double single. And hence the double was a double panel, so double truss, double story. And so that is where the acronym double came from, not from Tim Hortons. I'm not sure if Tim Hortons stole it from the engineers, but you still hear that terminology. You'll hear triple. Somebody wants 3 creams and 3 sugars. But a triple would be a Bailey Bridge, 3 trusses wide, 3 stories high. Now, the next slide I'm going to show you is to give you a sense of the load capacity. And so this is the military load class. And I know there are a lot of numbers on this slide, but the intent behind it is to give you an idea of the load capacity, how it increased based on the configuration of that bridge. So the first 3 numbers that you see in here circled in green will be typical vehicles that we're used to today that you would see on a Canadian road or a British road, an American road. So you might have cars, medium trucks, tractor trailers. And a heavy truck would be, say, a tandem truck filled with rocks that might be involved in a construction site. The vehicles you see lower down that, circled in red, will be now your military vehicles. So now we're looking at tracked vehicles, because tracked vehicles are significantly heavier due to, obviously, the metal that's part of them and the iron. And so you get into armored vehicles and then tanked vehicles. So you can see here how that maximum span of that bridge, say if we look at load class 50, if we have a double single bridge, you could only have 18 meters or approximately 60 feet, versus all the way up to 55 meters if it was a triple bridge. So this was the amazing flexibility of Bailey's design. I mentioned earlier about variations. Not every gap is going to be a dry gap. And so the unique nature of this bridge is that there were 4 basic variations that you could have. You could have a single span bridge, or you could have a multi-span bridge that would use perhaps existing piers. You may have to repair those piers to span greater gaps. Those would be used to replace a bridge that had been destroyed by enemy forces. There was also a floating or a pontoon bridge, which was pretty cool. The bridge would be built on pontoons in sections and floated into place and then linked up. And so these were the types of bridges that would span, say, the Rhine or span the Arno or the longer gaps. And then there were these two at the bottom were used. It was a suspension version, believe it or not. And it was developed in 1943, and it was quite often used in Asia because it could carry a slightly wider gap, but it was very useful in rugged mountainous regions where piers couldn't be constructed. So in Nepal, in northern India, when the forces started to retreat and advancements started to be made in those areas. And then the lift bridge, if you can believe it, was developed. And that was particularly important because the canals were necessary to move materials as the forces advanced through Europe. As many of you may be aware, there's quite an extensive canal system in the Netherlands, in France, in southern Germany, and Western Germany. And so this lift bridge was developed to replace very low temporary spans over canals. So in total, over 600 firms were involved in manufacturing this bridge. Over 500,000 tons, that's not metric tons, were eventually constructed of the Bailey Bridge, all to support the war effort. So now back to another part of the title, the Royal Engineers. The Royal Canadian Engineers have been around for a little over 100 years. And the Corps, if you like, itself was formed in 1983 out of militia units. Before that particular time, you would have some professional soldiers, you would have ad hoc militia groups. In fact, here where I live in Ottawa, one of our most famous pieces of infrastructure is the Rideau Canal, which was built by the Royal Engineers and Lieutenant Colonel John By. But in 1983, all of these units came together to create a regular force unit, and that became known as the Royal Canadian Engineers. By the time the Second World War came about, you can see the ranks had swelled to what you see here, 680 officers, almost 16,000 other ranks, from sappers or privates up to chief warrant officers. And these engineers punched well above their weight, as you're going to see in the next few slides. Canadian Army war effort was assigned, among many things, to building Bailey bridges to support the advance through the Italian campaign, in through Sicily, and into Northwest Europe. The three battalions that formed part of this establishment took on the construction of many of the major bridges in World War II. And during that time, the basic unit was a field company or a field squadron, and it would have had 7 officers and 249 other ranks. So that was who would be involved in building these bridges as a basic unit. Today, we've got approximately 6,000 reserve and regular force members across Canada in various FERs, or field engineer regiments. So that's who the engineers were and who they are now. But let's look at the Bailey Bridge and the theater operations and what role the Canadian engineers played in that. So I mentioned Bailey's Bridge could be built in under 4 hours, in ideal conditions, 8 hours at night. Well, clearly those were not going to be the ideal conditions. It was rarely the case. This is a picture of the Royal Engineers building a Bailey over the Rapido in Monte Cassino. And to me, it just really epitomizes what that area would be like. I mean, if you can just close your eyes for a moment, in this picture, you've got light. If you can imagine smoke and gunfire, the loudest noises you've heard, like thunder and rumbling and flashes, and all that, you're supposed to keep your concentration and build this bridge. And so this painting really vividly displays what they might have gone through. The night, the enemy fire, the less than ideal ground. I mean, you can look here, it looks like a swamp. And this was very typical of what might have been encountered when these types of bridges were built at night. So let's take a moment and look at some of the construction. I'm going to focus more, obviously, on the Canadian engineers, but there were some very interesting bridges that were built by the Americans and by the Royal Engineers. The River Majerda was one of the first bridges built in 1942 in the North Africa campaign. And that particular bridge is the one that was being built when I referenced that soldier, that sapper earlier. That quote came from the building of the Majerda Bridge. And it was a double single bridge. And you can see here sort of the gap that it spanned. Then we started to get into some of the more interesting designs of the bridges. So the bridges over the Sangro and the Grub, for example, 2 completely different countries, one in Italy, one in India, built by the Americans and the Royal Engineers. And so now you start to see the pontoon bridges were built. And then the Tyne and Tees was quite a major bridge. I believe this was one of the longest bridges built at its time. And it was built on existing piers. So there had been some piers in place that either had to be repaired or they could build this bridge and launch it over those piers. And then here's an example of one of the suspension bridges that was built in Burma. And this is the Shweli River, would have been built by the US Army. And that was one of the rare examples of the suspension bridge that was built. And so again, you can see the length. coming back to our theme of the Royal Canadian Engineers, perhaps the greatest role that the RCE played initially was in Italy, in Sicily, in the Lira Valley, and as the Gothic line was breached and the Axis forces were retreating out of Italy. Now, you'll see two here are starred, Leonforte and Blackfriars, and I'll come to those in a moment. I've got two special slides about those. But Ortona, a triple single bridge, was built by Fore Field Company, and you can look at the length here. The Winston and the Churchill bridges are quite interesting. The RCE supported the push towards Germany, particularly through the Netherlands and into northern Germany. And these two bridges were built. One was called the Winston Bridge, the other the Churchill Bridge, and they were across the Orne in northern France. There's a really good picture. I didn't put it in here because there were so many pictures I had to choose from, but there's a great picture of Winston Churchill driving across, I think it's the Churchill Bridge, in his Jeep sometime in 1944, late 1944. The Walsh Bridge, again, the Maas was quite a large river that had to be crossed, and you can see the length of that one. That would have been a pontoon bridge. But the Jones and the Tatham bridges were also interesting because I'd mentioned about the canal steel being necessary to transport materials. And so the RCE, because of their expertise, they were instructed to build two lift bridges and to decide what the best design was. And so they tried the two design. One was named after Jones, who was the commander building that bridge, and one was named after Tatham, the other officer in charge of the bridge. What was interesting about these two bridges is that the Jones could be raised much faster, but the Tatham could be lowered much faster. And so that was the one that was chosen, and that was the design that they went with for all of the lift bridges that were built throughout the war. Now, I said I would come back to Leonforte and Blackfriars. Blackfriars was the Royal Canadian Engineers were asked to build a bridge to cross the Reese River in Germany. And at the time, it was the longest bridge built. Two 34-meter landing bays so the vehicles could get onto the bridge. You had these 34 connected spans, and this gives you a sense of the pontoons, how they were connected together. What was remarkable about this bridge is it was built in under 72 hours from this Bailey kit. And in fact, it was so successful that the officer overseeing the construction was awarded the Military Cross. When it was completed, it was the longest Bailey bridge built in the time. And I think it was superseded perhaps a little bit later on in 1945. It's certainly a feather in the cap of the Royal Canadian Engineers that this was such an amazing bridge that was built. There's a lot of words on this slide, and I'm not going to read them, but this is the plaque that was recently installed at Leonforte. And this bridge was built in 1943, and it has the distinction of being the first bridge built under enemy fire. So that picture that you saw at Monte Cassino, imagine that scenario when this particular bridge was built. When they went to build the bridge, they came across an enemy machine gun post, an infantry platoon, and despite all of that, they were able to build this bridge in 4.5 hours under enemy fire. It wasn't an overly long bridge, but it was the conditions under which it was built, and it was a critical bridge for this particular gap. And so some of the pictures that you see here, the map shows the exact position and what they were facing. There's a reconstruction to show what that gap looked like. And on the bottom left picture is what that bridge looks like today. Obviously, a Bailey is not there. But just in July of this year, there was a delegation of the Royal Canadian Engineers that went over to Leonforte, and this plaque in 3 languages, English, French, and Italian, was installed in honor of that particular bridge crossing. So the war started to wind up. These amazing bridges would have been dismantled. Certainly the pontoon bridges were dismantled. Some of the other bridges stayed in place for a while. But Bailey Bridge construction didn't end with the resolution of World War II. Following the end of the war, this massive Bailey stock that was in the UK and Europe was disposed of individually in the various countries. Many of the Canadian stock was sold to surplus through the Canadian War Assets Corporation, and public sector organizations bought a lot of this stock. In fact, one of the largest owners in the world for a period of time was the Ministry of Transportation in Ontario and the Ontario Hydroelectric Power Commission. So what started this modular temporary bridge became this lifeline for many. It was critical to rebuilding efforts during the war, either as a temporary bridge. It became part of natural disaster response. And we'll look at some examples of these in a moment in Canada. But its versatility was just phenomenal. And in fact, it still is used. One of the most recent Bailey bridges built was in the mid-2000s, and it was built in Australia across the Derwent River after the Tasman Bridge collapsed. The highest bridge in the world is still there. It's in India, built by the Indian Army in the Ladakh Valley. So it's a testament to the robust design of this bridge, how so many of these so-called temporary bridges remain in existence. And so we're going to look at a couple of interesting ones that are here in Canada, and many of the early ones still have that link to the Royal Canadian Engineers, because many of the people that left the service after the Second World War went into the private sector, the public sector, and they became the foundation of the engineers. So in Canada, one of the first bridges built, Hurricane Hazel, was a major disaster that rolled through the Toronto and the Southern Ontario area in 1954. The bridge you see on the right was built over the Rouge River. It's called the Old Finch Avenue Bridge. It was built in 1954 after the flooding from Hurricane Hazel washed out the bridge, along with many, many other bridges. And so the Royal Canadian Engineers were mobilized just as they are today in support of aid to civil power. And they went throughout Southern Ontario, building Bailey bridges to span these gaps. And so in 24 hours, you had a bridge that was operational and the traffic could continue to move. And in fact, this bridge is still in place. It underwent a retrofit and a strengthening of the deck in the early 1990s, but it's still there. You can still go, you can still see this bridge. The other one on the left was one that I hadn't even realized was there. I spent my high school years in Toronto. Many times I would go down to something called the Canadian National Exhibition, cross this bridge on Lakeshore Boulevard, completely no idea that it was a Bailey Bridge built by the Dominion Bridge Company in 1952. And in fact, it may still be the oldest public constructed Bailey Bridge in Canada. And then the Great Trail, the Trans-Canada Trail. Next time you'd go along it, take a look at some of the bridges on it, because as part of their centenary in 2003, the RCE was involved in constructing many small bridges along the Trans-Canada Trail, and a lot of them were Bailey bridges. I think the last one that was built was a double single Izzy bridge, and it was built in the Creston Wildlife Center in British Columbia. And that particular bridge I mentioned because it was named after Master Corporal Mark Izzy Esfeld, who was killed removing landmines in Croatia. The most recently built one is an 85-meter bridge across the Chidoki Radial Trail, and that was built in 2020. So, they're still being built and still being used. But one of my favorite bridges, so that's the public sector, one of my favorite bridges is the private sector. And this particular bridge, I don't know if any of you will recognize it, but it's the Kananaskis Bridge, and it's near Seabee, Alberta. It's interesting for several reasons. First of all, most Bailey bridges, the deck is at the bottom, and then you have the superstructure on top. But in this particular case, the deck was lifted at some point over the past 50 years to run midway between the panels. But it was constructed after the collapse of the original bridge. And as would have it, the general manager of the plant was a retired World War II field company commander. And he'd remained in contact with his wartime buddies. And when this bridge collapsed leading into this private plant, he called them up and said, hey, we've got to replace the bridge. Let's get a Bailey Bridge. So Ontario Hydro stock was used. And this bridge was built by retired RCE members for the Canada Cement Company. And this bridge still stands. I took this picture last summer. It hasn't been reinforced in any way. All the parts are still there. It is a triple-double. And at the time of it was constructed in 1950, it was the first and longest private Bailey Bridge built in Canada and in the world. And I think it is still probably the oldest Bailey Bridge in Canada. Ken will be able to correct me later if I'm wrong. I mentioned that the Lakeshore Bridge is probably the oldest public bridge. This is probably the oldest private sector Bailey Bridge that still exists. So what about the future of the Bailey Bridge? It's been over 80 years since Donald Bailey first designed that modular prefabricated bridge. Military engineers continue to use it to this day to support their own operations, as well as disaster relief efforts. And it's become a staple of many organizations that use it as a temporary bridge, a permanent bridge in hard-to-reach locations, or even as a trail bridge. You go back through Ministry of Transportation Ontario records, and you can look at how many times it was built as a temporary bridge when the Trans-Canada Highway was being built, certainly through areas in Northern Ontario. It's just phenomenal. To this day, it's part of the Canadian fabric. And even when it's no longer fit for purpose, like the picture you see on the right, there was quite a bit of debate in the news, certainly in Prince Edward Island, early on this spring when Hurricane Fiona went through and it damaged the Bailey Bridge that was there. And so what happened is that they want the Bailey Bridge rebuilt. And so you can see here from the sign that is on the bridge, it says Honorable Lawrence Macaulay, don't it, save our bridge. And it's not about that wooden bridge, it's about the Bailey Bridge that's underneath it that was damaged. The Bailey itself in this format has been slightly modified. It's not quite made the same way. Mabey Bridge is one of the original manufacturers of the Bailey, and they do continue to produce a modified version of the bridge. Acro is another company that builds the Bailey Bridge and also produces a modified version. Both can be installed and disassembled after their use. China still probably produces a large volume of the original Bailey design. And many other companies will make modular prefabricated bridges, but they're nothing like the Bailey Bridge that can be put together, disassembled by hand, and reused. The latest example I found here in Ottawa is a temporary bridge put in by OC Transpo. We call it the noisy one because it's a Bailey Bridge style or sort of similar design to a Bailey Bridge, but it rumbles so much that the local residents were quite perturbed when this bridge went up. So I had to run out and take a picture of it just to show you that how that design is still there and it's still out there. And I think the reason this is such a great history topic is that legacy of Donald Bailey can't be overstated. This simple bridge that was first sketched out on the back of a napkin by a man that was a model enthusiast, it developed into something that was instrumental in supporting the war effort in World War II. And even beyond that, in the past 50 years, we've seen what has happened. So it's become ubiquitous around the world, wherever it or a version of it's built. And as for the Royal Canadian Engineers, well, their motto is UBEAC, which is Latin for everywhere. I think that's rather fitting because it's just like the Bailey Bridges that they've built. So I'd just like to close with some acknowledgements. The Canadian Military Engineers Association was phenomenal in supporting this paper, and also the Canadian Forces Military Engineers Museum, and our various colleagues from the Ministry of Transportation and the CSE Bridge Task Group, who also provided some additional information for this. I'd like to thank you, and I'm going to turn the floor back. Before I do, I mentioned the Bailey Bridge is ubiquitous. This picture I took last fall when I was in Uganda doing some work, and I was driving through Murchison National Park with my colleagues, and I turned my head to the left, and what did I see? A Bailey Bridge. So thank you very much for your attention. I'm happy to entertain questions now. I'm going to turn the floor back to Cole, and he will introduce Lieutenant Colonel Holmes, who's also here with me to help answer some questions.
Thank you, Linda. That was fantastic. Like Linda mentioned, we're going to move into our question and answer period. And to help us with that, she's invited her co-author, Ken Holmes, to join us. Ken joined the Canadian Forces Regular Officer Training Program in 1961 and graduated in chemical engineering from the University of New Brunswick. He served in various roles with the Canadian Forces, including Troop Commander, Platoon Commander, Commanding Officer of CER in Lahr, Germany, and various subsequent senior staff officer appointments. Since his retirement in 1992, he has been a volunteer researcher at the Canadian Military Engineer Museum and is an author or co-author of 5 books. The CSCE National History Committee is delighted that Ken attends their monthly Zoom meetings. Welcome, Ken. To those of you online, to submit questions, please use the question function in the Zoom, and we'll address as many of those as we can. But first, to kick things off, I was going to ask, Linda, you talked about Leon Forte Bridge in particular. During the deployment of that bridge, was there any way for the soldiers to be protected from enemy fire? Were they out in the open during that battle?
Is that one, Ken?
No, there's absolutely no way to protect them. You almost can't even wear a helmet because that gets in the way of the work that you're doing. One of the secrets is secrecy. You build a bridge like that at night, hopefully with a fairly dark cloud cover, and it's done as quietly as possible. The hammers that are used to drive in the pins that connect the panels are hide-phased hammers, so it muffles the sound. So you try to do it in secrecy. If you are discovered and there's direct fire and indirect fire, then you work through it the best you can. And when it becomes too heavy, then you have to abandon that site and construct a new bridge somewhere nearby.
Here's a question from Gordon Masterson. He's wondering if the Axis powers developed any similar prefab bridges. Did they endure? Are they similar to the Bailey bridges, or are they different in any particular way?
No, they did not develop anything like the Bailey Bridge. I think their efforts were concentrated on destroying bridges and withdrawing, not advancing.
Mm-hmm.
Their advances were generally done with armored vehicles across existing bridges into Axis territory.
And in fact, it certainly did help win World War II. Anytime you read any literature about the Bailey bridges, you'll get quotes from Churchill and from Montgomery and from Eisenhower to say they could not have won the war. I mean, obviously it was not the sole thing, but without the Bailey Bridge, there would have been certainly significantly more loss of life, and the war would have gone on much longer. You wouldn't have been able to get across those gaps and continue the advance.
You spoke to what the deployment was like for some of those bridges, how they got out onto existing piers or across narrow canals or broad rivers. What was it like on the supply line side or the organization? The issue of getting the right parts to the right place at the right time. What was that work like behind the front lines?
Extremely complicated and very well planned. Like Linda mentioned, the bridge components themselves were manufactured in some 600 different plants and many small plants throughout England. The Americans also built the bridge, and Canada built a number of sets of bridges and delivered them for the war effort. But the resupply really started at these individual factories and continued all the way to the individual bridge site. Everything was planned extremely well in advance from the highest level down. Bridges were basically accounted for in terms of sets. So in terms of managing the larger numbers, we were talking about a collection of all the bits and pieces that would build about 120 feet of bridge. And the senior planners would know weeks in advance how many sets of bridges they were likely to require, and the equipment would be gradually moved forward. So when the individual troop commander, squadron commander, or company commander identified the need for a 50-foot bridge, he didn't have to phone London to get the bridge on its way. The equipment was already on its way because the senior planners had ensured that those logistics requirements were properly addressed.
And if you think about this, what would happen is, these, for the most part, they wouldn't say, well, next week we need a bridge, tomorrow we need a bridge here. It would have been, they'd have known where the advance was going to go and where they were planning to go. So they'd have an idea of what those bridges were going to be so they could plan that. Certainly you would come across an incident where you may need one immediately. The other thing that was unique is that, like anything that came 50 or 60 years ago with the British or with the Canadian forces, it came with a manual. And so this manual would tell you, you would look up, oh, this is my gap. This is the load I think I need. And it would tell you how much kit you needed for that particular gap, what type of bridge you would need. It came with how you needed to construct it. I mean, this would have all been practiced back well behind the lines. So it was almost like an assembly operation. It rolled up and there it was, and you used it, and it was timed, and then it was disassembled and moved on to where you needed it next.
Are there any estimates for how many of these bridges were produced or deployed during the war?
In total, it's estimated that there was enough bridging equipment manufactured to cover 200 miles of the fixed bridging at about 40 miles of the floating bridge. In terms of the numbers of the actual bridges, in the European campaign, there were about 2,000 individual bridges built. And in the Italian campaign, it was even larger. There were something like 2,500 bridges being built. So huge numbers of bridges.
Again, these wouldn't have been left in place. So these would have been built and then deconstructed. Some cases they may have been left in place, but certainly where they could be taken back, they would have been disassembled once a more permanent structure could go in place. So I think we had something like 700,000 panels were constructed. You imagine that, almost 1 million of these panels, these 6-foot Bailey panels.
Now, Linda was talking about some of the older bridges in Canada. I believe the oldest bridges are actually in the Yukon Territories and Northwest Territories as part of the effort along the Alaska Highway. There were oil fields up in Norman Wells. And in order to access that oil and to get it out onto the Alaska Highway, Bailey bridges were built. Some of those bridges are still sitting there now. They're not, they're well off the beaten track and they're used by
Mhm.
recreational vehicles, but they have lasted since the 1940s.
That actually dovetails nicely into a question we have from Richard here. He's wondering, since these were robust and easily erected bridges, besides the example you gave for the Alaska Highway and the oil fields, were there other examples of these kinds of bridges being used for temporary construction works?
Absolutely. I mentioned that the Ministry of Transportation of Ontario and Ontario Hydro took up a good chunk of the inventory. And so they were used as when the Trans-Canada was being built. These bridges would be put in and were used to span gaps as the roads were being constructed. We made reference to natural disaster response, where bridges would be washed out. And that's typically what would be in the engineer's toolkit. Now they've got a different type of bridge that's used, but a bailie would go in and be there as long as was needed until the public sector, or in some cases the private sector, could rebuild the existing bridge. There's some really great pictures in the MTO archives where they're going to twin a road. And so you see the old bridge, you've got a bailie bridge that's gone in. And if they're going to be reconstructing a bridge or repairing a bridge, they put the bailie bridge in, and then they do what they need to do, and then the bailie gets dismantled, and then the other bridge gets built.
You mentioned that in war conditions, they were limited with the kinds of materials they could use, and so they primarily stuck with steel for post-war construction for some of these other conditions. Did they ever use aluminum to change the for lightness and durability uses, or do they pretty well stick with steel?
I think it's been steel, hasn't it? I'm not.
Certainly the majority of the construction has been steel. The original construction was a particularly high strength steel when they built it, when they designed it in England. When the Americans started to build bridge, they used an even higher strength steel. Some of the modern bridges are using much more sophisticated materials, but if you're looking at the mass production, Linda mentioned China.
They're using steel.
The amount of bailie bridge using just good strength steel it's a huge number that's still being built.
And the reality is that because of its modular construction, even though it was steel, 570 pounds or what, 230 kilos or so. Now they're not built to the same extent by hand, that the parts are moved in, but it's still not a heavy panel to bring, even though it is made of steel. I don't think Acro is using aluminum. I think they are still. I'd have to know. There may be somebody on the panel that is from Acro, or maybe, but I think they are still steel, but just not the same grade.
We have another question kind of about the details of launching the bridges. This one's coming from Phil, and he's wondering if when the single spans got launched, did soldiers have to be on the far side of the span to catch the nose section, or could that just kind of be dropped on the other side?
Yeah, it was just dropped. Yeah, you might have had somebody over there just keeping an eye out, but this was the whole intent of this bridge, is that you could push it over the gap and then it could land on the other side.
No, it lands on a set of rollers.
Somebody would put the rollers out, obviously.
You continue to push the bridge across basically until that nose, that light construction is beyond the rollers, and then it's jacked down onto the permanent mounting of a base plate.
You would have a minimal amount on the other side. Somebody would have had to have got over to set the rollers down, but you certainly wouldn't have had a troop's worth of sappers on that other side until you were secure, that you knew that area was secure, and then that you could start moving.
So most of these bridges, when they were originally deployed, the intent was to be quick and temporary, but you talked about how a lot of them ended up being permanent structures. Did they require any common modifications to become a permanent structure? And if they did, are there any unusual maintenance requirements attached to any of those?
No, you may have had to firm up the approaches.
Occasionally you would replace basically the temporary bank seats that they're on with a more permanent construction. As an example, the base in Petawawa built a large bailie bridge into an area that was commonly used by the public. Very often fishing expeditions were underway around it, and young kids would do things like try to undo some of the things that were bolted. So the modification,
it was meant to be disassembled.
The modification there was a little bit of tack welding, and that was about the sum total.
Because it was robust enough. You might have to replace the decking at some point. check the bridge if you had rust in certain spots, but as Ken said, it would be primarily the approaches and the embankments that you would have to really fortify for it to be permanent. And that's about it.
Do the replacement parts for those, when they're needed, come from any particular firms? Are they being produced anywhere in particular?
They were stockpiled. So I suspect MTO still has a stockpile
Yeah,
of them.
most of the highway departments maintain a supply of them. Supply is running out, and in many cases, they're replacing it now with the Atco Bridge, which is quite a similar design in terms of the truss design, but not specifically designed to be built by hand. It's unusual to see Bailey built by hand anymore.
No.
It tends to be built by crane. But the Canadian Forces stopped using the Bailey Bridge around 1990, the early 90s. It was taken out of use by both the regular force and the reserves. We use much more modern bridges, like what's called the medium girder bridge, that can again be built by hand, but
A little lighter. Yeah. What's remarkable is that, even 50 years on, those parts were manufactured, that the tolerances were so exact that they could have been made anywhere and they would still work and still come together. There was one little hiccup Ken was telling me about. The Canadians gave the jigs to the Americans, but they made copies of them. And in those copies, the tolerances were slightly off. And as a result, there was a series of panels that were made. You're saying, Ken, the parts that they didn't fit.
yeah, so there was something like 800 panels ended up in the European theater, and they simply couldn't fit properly with the other panels. So there was great consternation as they tried to figure out what to do with the panels, and the idea came up, well, let's just use them as a separate, different set. But it was appreciated very quickly that there was no way that they could keep those panels identified as being different, so they were quickly withdrawn from use.
Ken, I know you said that these aren't being deployed by hand anymore, but are there still examples in current conflict zones of these kinds of modular bridges being deployed?
Yeah.
I think one of the areas that you see them built by hand mostly is in Asia. It's surprising the number of Bailey bridges that are used to provide access into the mining areas, into the logging areas, and they're very difficult sites to get into. Those are very often still built by hand.
It's amazing once you're aware of the configuration. I would drive my family nuts because we'd be going somewhere. I go, oh, it's a double-double. And they go, no, Mom, there's no Tim Hortons here. Or look at that double single. And they go, what is she on about? I said, I saw that bridge in Uganda, and you just suddenly become aware of it. And then you realize just how ubiquitous they are. They're everywhere. There's some interesting comments here I'm seeing in the Q&A, a Bailey Bridge in Little Southwest Miramichi, and then another one here is temporary bridge in Paisley. Half the time, if you're not aware of them, you don't even realize that's what they are, other than it looks like the last one you saw.
Well, we're approaching the hour here. I have probably a good question to end on from Gordon. He's wondering if there are any authoritative texts or references for further information, other places where they can get some information on Bailey bridges.
I will drop the Canadian Military Engineers Association history site into the chat.
Perfect.
And that's a really good starting point. There's some of the references. thinkdefense.co.uk has some great information on Bailey bridges as well. It's somewhere we got some good pictures from. I'll just pop that into the chat while you're doing your wrap up.
Perfect. Okay. So thank you everyone for joining us. Our next webinar in the new Transatlantic Cable series will be in the same time slot on Wednesday, November 22nd. ICE panel on Historical Engineering Works member Sue Threader has graciously agreed to present a webinar called Dealing with the Bends, the History of Pneumatic Caissons for Bridge Construction. Be on the lookout for details and an announcement coming late in October on that one. Meanwhile, please pencil in that date and time slot on your calendars. And then finally, here's the second code word to select in the post-webinar survey to receive your PDH certificate. The word is Telford. Please don't terminate your connection until the webinar ends. At the end of the webinar, a Zoom window will appear. Please click on that to go to the survey, which you'll need to complete within 30 minutes. You should expect to receive your certificate in an email from the CSCE National Office by the end of the week. Please check your spam filter if you don't see it, just in case. So with that, thank you all again. We look forward to seeing you in November. Have a happy and productive autumn in the meantime.
The new transatlantic cable webinars are coordinated by a tripartite ad hoc committee that includes the individuals listed here.